What's up, everybody? We're back. Tom McGurl stream here. We're going to be kicking it off with Chapter 6 today of the Rust programming language book. We're all on our journey to become Rustations. What up in the chat? Shout outs to Bacow. We got Virtual Boza, Clam Watson. Happy that you're all here. Today is going to be a fun day. We're learning about enums and pattern matching, two pretty cool concepts to Rust. Concepts you might be familiar with from other languages. You wouldn't be familiar with if you're using something like JavaScript, because there is no pattern matching. But if you've used other languages, Elixir, Elm, some functional languages, it's going to be pretty fun. Enums, the digital version of nums. Yes. So again, if you're catching us for the first time, we are on Chapter 6. We've been going through all of the chapters. If you missed any of the previous chapters, do not worry. We've got you covered. Over here, we got the YouTube channel. You can find it. Just search Tom McGurl. The channel link is a little long because I don't yet have 1,000 subscribers, but who knows? Who knows what's going to happen tomorrow? So we got chapters. You can see part 1, 2, 3, 4, and 5. We covered a little bit of Chapter 6 last time. We'll recap that. Also got a session here on serving up a serverless backend with AWS Lambda, DynamoDB, and TypeScript. So check that out if you're interested. And also our previous sessions on building a React Native app with Expo. React Native, obviously, React, and Recoil.js. We also use TypeScript for that one. So that's a longer series, but pretty fun. If you're interested in learning about Recoil.js, we had a good time learning about it. But now it's all about Rust. We're going through the book. What book, you might ask? We're going through this book here, the Rust programming language. Last week, we shouted out the authors of the foreword, as Clam Watson pointed out, instead of the authors of the actual book. Oh. But this time, we're going to give a shout out to Steve Klobnik, Carol Nichols, and the other folks from the Rust community who contributed to make this awesome book. We couldn't be here doing this without you. It's been an awesome guide, super thorough. I feel like I've learned a lot, and we have so much more to go. As everyone who's been watching knows, Chapter 10 is going to be nuts. A lot of stuff we've been reading. It's like, we'll cover that in Chapter 10. Well, I'm looking, Chapter 10 better come through, right? Better come through with some real learning. But today, it's all about Chapter 6. So let's dive right in. Without further ado, again, if you want to get notifications real quick, follow me on Twitter. I post notifications on when I'm going live. It's a good place to follow. Also, all the code we write here today will go into this repository, Learn Rust Live. I push it up after the event before posting the video on YouTube. So feel free to pull that down and catch up on where we're at. You'll have to do some basic Rust setup, but that's all covered in the first chapter of the Rust programming language book. And if you don't feel like installing Rust, use a Docker container. There's plenty of great ones on Docker Hub, so check that out. All right, Chapter 6, enums and pattern matching. The first part here is going to be a bit of a recap because we started it, but let's go through it really quick because it's a good foundation to move forward with the rest of the chapter. So what is an enum? Similar to a struct. So we covered structs in Chapter 5. Structs were kind of like almost like declaring a type in TypeScript. Where you can declare a type that's made up of different properties of other different types, or you can think of it as kind of like an object, almost like a class definition. And we talked about how you can have functions in that, or what we call methods, and those go inside the implementation block. But now we're talking about enums. The first thing we covered last time was the good use case for enums. So one of the suggested use cases that they gave was IP addresses. And here you can see on the left, IP addresses can have two forms. Let me actually zoom in a bit so you can see this a little bit better. So the forms that we can have are we can have an IP address version 4, which is going to have basically four different unsigned 8-bit integers representing the IP address. That's probably something that you're all familiar with if you've ever typed your IP address or tried to log in your router 192.168.1.1. and so forth. And then the version 6, which is a string in this case. So what we've done here is they created an enum with these two types and showed us how to create an instance of that enum. So here's an IP address version 4, an IP address version 6. Then we dove in a little bit more and found out how to expand that. So here they've compared it to a struct, where you have a struct and you're saying the kind of this IP address struct is of type, and they're referencing the enum, and the address is a string. So you have a structure wrapping the string that represents the actual IP address, and then the kind, which represents the type that the IP address is, either version 4 or version 6. Then we saw how to go a little bit further. How can we declare that string as actually part of the enum? And that's what we have here with this IP address. So we're saying it's version 4, and it's going to take a string. And so we've instantiated home, which is 127.0.0.1, aka localhost. And we've used the string from to create that string. And that's of type capital S, and that's what we have here. Then we've created a version 6 of that as well. Broke it up even further. So instead of just using strings, we broke it up into actual types. So our v4 is 4 unsigned 8-bit integers. Again, because it can only go up to 256, so an 8-bit integer is actually perfect for this. And so we have our version 4 here, and then our version 6 remained a string. We then went in a little further to see what the actual implementation of IP address is in the Rust programming standard library, as well as created another example. So here, the other example was a message where we had a quit, move, which took 2 coordinates. Both are signed 32-bit integers. Write, which is a string, and change color, which takes 3 unsigned 32-bit integers representing red, green, and blue, respectively. So here we can see how we use that. We have a struct. This is the same enum up here, but in struct form. This is what it would have looked at as a struct. So it's a little bit nicer up here, you can see. And then here we learned about how we can actually add methods to structs. So again, using an implementation block, we can add functionality. So message write, and then we can call functionality or methods on that enum. Commander thrashed in. How is Rust so far? I've been enjoying it. I'm sure other folks in the chat could tell you how they've been enjoying it. It's been a lot of fun. It's definitely a little bit of a learning curve, but that's why we're going through it together. That's why I have all of you here. I was like, I could do this on my own, but why not do it live? But so far, so good. So you can see here we're able to use self because it's the body of the method, just like we were in structs. Then we learned about some of the enum, basically like what makes it advantageous, right? And so one of the things that came up was the option enum. Trice Tank, what up? Happy to have you here, Tank. Always happy to have Tank. All right, so here we learned about the option enum. So the option enum was similar to like a maybe type, if you've used those in other programming languages. It basically represents the presence or absence of a value, and it can be of any type. So that's why we have this generic T. So in this enum option is an option that takes a generic type, so you can say what kind of option it is. It could be an option of a string, could be an option of a struct, could be an option of another enum. It could be an option of an integer, anything. And then the other value is the absence of that. So there's no null in Rust. We talked about last time that famous JavaScript quote that the null was the $1 billion mistake because it's potentially caused companies billions of dollars in exceptions and errors in the past. And I'm sure that's probably not inaccurate. So the none type is going to prevent us from using null, and we can actually use the absence of that value. So Commander Thrashin said, wait, I think there is, like in unsafe. I'm not sure. We haven't covered it, but in this, they did mention right here that null is a value. That means there's no value there. In languages, null values can always be in one of 2 states. Talks about the problem with null. Concept of null is trying to express it. Still a useful one. A null value is that currently invalid. And that's why they don't have it as part of Rust. So Rust does not have nulls, but it does have an enum that can encode the concept of value being present or absent, the option. So the syntax here for T, it's just talking about generic, and we can see here's an example of sum with a number. So sum 5, sum a string, absent number is an option I32, and we can set that to none because we've declared that it's an option of type signed 32-bit integer. The null problem, I only learned last year that in Java, they consider null any class. Yep. So it's, I mean, all the languages I've used have had a concept of it. Elixir, you had nil, JavaScript, null. In Python, you have none, but it's not used like this. It's not used in a safe way, I'd say. So if we use none rather than some, we need to tell Rust what type of option we have because the compiler can infer that the type of some variant will hold by looking at the none value. So it knows the type. So it knows it's either there, and if it's not there, what would it be if it was there? And that's going to give the compiler some inference so that it can properly compile. And so here we see our Rust station, and she is looking great there on the right. And we can see that the question mark is the code does not compile. So we'll see that this doesn't compile. So we have X, which is a signed 8-bit integer. That's the I, 5. And we're saying that Y is an option of type signed 8-bit integer. and we're declaring it as sum5. And then we try to add those. It's going to give us an error because it's going to say, hey, y may not be defined. It might be none. And I can't do math with none and 5. And so that's why we're doing that. And so here, down here, we see the error. No implementation for signed 8-bit integer, standard option I8. So tells you right here why it can't do it. And this is because it's not present. So pretty cool. The option type is super powerful. We've dealt with it before. We've seen this. We've seen another important enum that I want to call back to, and that was the result. So I'm just going to pull up here on the right. Let's pull up our guessing game. We always go back to this one because they had us do it early on to kind of show us some of those concepts, and it's been extremely useful to reference back. So here we have our function called parse, and parse here returns a result. And so we're using pattern matching, which we're going to learn more about, because it can have two different options. It can have OK, where it actually contains the number, or error, where it doesn't contain the number, it contains an error. So that's going to be something we'll go into where we see that. I wonder if I highlight this, if it'll show me what it does. Let me try doing this, see if I can get the docs on it. Let's see if it'll give me a little... So I feel like my Rust thing is not working because last time it actually did show us, but we'll try it out. So what we can do is we can go to Rust lang, and then we'll search parse. Do a little search for parse here. Here's parse. And we can see parse returns a result. And so that's what we're referencing. So a result can be of type OK or error. So pretty cool. All right, so let's go on to the next chapter. So the match control flow operator. So we've used this before. Again, you can see it here on line 21 where we've matched on the options, or sorry, not the options, the different basically properties that an enum can have. In this case, we matched on OK or error. So let's dive in and see what we have here. Rust has an extremely powerful control flow operator called match that allows you to compare value against a series of patterns and then execute code based on which pattern matches. So here, if we had our OK pattern, we return the number. If we had the error, we printed the error and continued our loop. Patterns can be made up of literal values, variable names, wildcards, and many other things. Chapter 18 covers all the different types of patterns and what they can do. The power of match comes from the expressiveness of the patterns and the fact that the compiler confirms that all possible cases are handled. So it wouldn't compile had we gotten rid of this case. So if we got rid of this case and we tried to run this program, it would let us know that it's not going to compile because we're missing that case. And we could even try that. So if I go into my projects here, let me toss myself over here so I'm out of your way. We go into projects, we're going to go into guessing game. And then if I do cargo run, let's see, am I in cargo run? No. Let's see. Cargo. We have my cargo. Did I not install it? Let's see. Rust C, is that there? Oh, Rust isn't there either. Interesting. It might be because I might have to change my... I'm using Windows here, so I have my Windows Subsystem Linux, although I think this is the same one. But let's see. Let's go into developer, learn Rust Live, projects, guessing game. So it's saying cargo is not found. So let me just go ahead and go back really quick and install that, see why that's happening. So that's easy. I'm just going to jump back to installation, make sure I have it all installed. Let's run this. Sorry about that. All right, let's see. Whoop, why is that not happening? Copy, do it the old way. All right. Let's proceed. So there you go. If you haven't seen how to install Rust, now you're seeing it. All right. Probably why you weren't getting help from the editor. Yes, that is probably correct because I didn't have Rust. It didn't have the language to actually pull from it. Good point, because it would also usually show the docs, which is really cool. Okay, so now we're going to just run, we're going to update it. So we're going to run Rust update. Oh. This isn't great. Let's see, did it? cargo's bin directory in your path. Let's do this. Oh, let me add it to my path really quick. Close the terminal. I did. Let's see. You know what I'll do here? Let's pull up my Windows terminal. Go into Ubuntu. Ah, there we go. I wonder why. Or source. Yeah, I can source the... All right, so let's do this. Let me move this here. Thanks for the tips, duders. All right, so let's zoom in here a bit and we'll run it here. So we'll go to projects, guessing game, cargo run. So right now cargo run is grabbing the crates. Thanks, Commander Thrashton. Hope you enjoyed watching the install. Yeah, I probably do need to close VS Code. Let me do that while this is loading. Let's do that. Close that up. Load VS Code back up. It's going to connect to my Ubuntu. There we go. Rust C. Interesting. Very odd. Well, either way, we have it running here. I can fix that later. So here you can see error is not covered. So this is exactly what we're looking for. So it's telling us parse pattern error not covered. And that's because we need to handle all cases. So let's do that. Let me just go here. All right, so let's put back our error. So here we say error, we take the error type. It doesn't matter, we're not gonna use the output. And what we're gonna do is we're just gonna put print ln and error occurred. Or we'll put, you know, it's usually if they entered an invalid number. Please enter a valid number. And then we'll continue. And again, we need to put a semicolon here. Now, if we go here and we do cargo run, oh, there we go. Well, I think it's because I forgot to include my, clear that out. Cargo run, let's see what it says. Expected comma, because I need to have a block here. There we go. Let's run that again, cargo run. And there we go, please input our guess, 32. So our game's working because we're handling that error scenario. Pretty cool. All right, so next up, let's see. Let me move myself back over here. Now that we've installed Rust, back to part 1. All right, so think of match expression as being like a coin sorting machine. Coins slide down a track with variously sized holes along it, and each coin falls through the first hole it encounters that it fits into. So with pattern matching, it's going to check each one from the top down and see which pattern it matches and then go into that code block. That's a really cool way to talk about it. In the same way, values go through each pattern in a match, and at the first pattern the value fits, the value falls into the associated code block to be used during execution. Awesome. Because we just mentioned coins, let's use them as an example using match. We can write a function that can take an unknown United States coin and in a similar way as the counting machine determines which coin it is and return its value in cents, as shown here in 6.3. So let's go ahead and create that. So what I'm gonna do is I'm gonna create a new project to run this code. Oops, so let me just exit here. Whoa. There we go, sorry. Wrong key binding. Okay, so I'm going to go back here and I'm going to create a new project, cargo new. We'll call it coins. And then here we have our coins project. Let's open up the main. Perfect. And so let's create this enum. We'll create it out here so that we can use it wherever. Coin. We have penny, nickel, dime, quarter. Perfect. And then here, we'll just use our main function to call our other function. So we're gonna create this function value in cents, and it's gonna take a type coin. So the argument coin is of type coin. That's what we have there. It's gonna return an unsigned 8-bit integer. unsigned because we don't have negative currency, right? I know some of my friends in the chat might be from Argentina. They might have negative currency. Oh, no, I'm just kidding, but we all know. So I'm going to go ahead and match on coin. And so here's the match statement. So we're going to specify each different type, and when it meets it, it's going to print that thing, or it's going to return that value. So coin, if it's penny, right, then we're going to get 1. If it's nickel, we're going to get 5. If it's dime, we'll get 10. Oop. And if it's quarter, we will get 25. And what I'm going to do here is I'm going to call, well, I'm sure they'll have us do it down here, so I'll wait. All right, let's break down the match in the value sense function. First, we list the match keyword. We've done that before, followed by an expression, which in this case is the value coin. So that's this. It's saying, what are we matching on? Coin. This seems very similar to an expression used with if, but there's a big difference. With if, the expression needs to return a Boolean value. But here, it can be any type. So we're not looking specifically for a Boolean value. We all know how valuable a peso can be. Tank. Yes, that's why we got to go down there. Beers are so cheap. So the type of coin in this example is the coin enum that we defined in line 1. So we can actually leverage that. Next are the match arms. So that's what we call each of these blocks here, 15, 16, 17. We call those the arms. Some other languages, you may call them branches, but in this case, we call them arms. An arm has 2 parts, a pattern and the code. And as you saw in our error, the code could be a code block. It doesn't need to be a single line. And they're separated by that operator. The code in this case is just the value 1 for penny. Each arm is separated with the next with a comma. So there's commas separating each of the different arms. When the match expression executes, it compares the resulting value against the pattern in each arm in order. So it's going to start at penny and say, does it match that? Print 1. If not, go to nickel. Does it match that? Print 5. If not, dime, and so forth. So it's going to check each of those arms. If a pattern matches a value, the code associated with that pattern is executed. If the pattern doesn't match the value, execution continues to the next line or the next arm. Much as in a coin sorting machine, we can have as many arms as we need, right? Our match has 4 arms. So it's going to fall into one of those. The code associated with each arm is an expression. So that's this code here. This is an expression. That's why we can have the block, right? And the resulting value of the expression in the matching arm is the value that gets returned for the entire expression. So again, we don't have a semicolon here, so we're returning this entire match, which will return this value. Pretty cool. Curly brackets typically aren't used if the match arm code is short. We use a single line like we have here. If you want to run multiple lines of code in a match arm, you can use curly brackets. That's what we do with error. So that's what we just saw. For example, the following code would print lucky penny every time this method was called with coin penny, but would still return the last value in the block 1. So we can do that. Let's add that. So here we'll just add a block, right? We'll print ln lucky penny. And semicolon there, and no semicolon here because we're going to return this expression. Again, we could also do that, but it's nice shorthand to just do that. Implicit returns. Patterns that bind to values. Before we hop into that, I don't know if they're going to have us do this, so let's try this out. We want to try this code out, right? So what we will do is we will call value in cents, and we'll pass it. We'll create a new coin. So we'll say, let penny equal coin, and we'll say it's going to be coin penny. And so what we're going to do here is we're going to pass penny here, and we will call this function. So we'll just go ahead here, and we'll go into our coins, and we'll do cargo run. Variant is never constructed, dime, quarter. Okay, so it's saying that, hey, you never used these. You never created a nickel, dime, or quarter, and that's because we only created a penny. But here you can see it printed out lucky penny, and it would have returned the value 1. So if you want to see what that looks like, we could say let result equal, we're going to get that 1 back, and then we can print ln the result was and penny. And so now we'll run that again. Let me just clear so you can see. Oh, and we're gonna get something funny here. Coin cannot be formatted. So coin is not what we want to print. We want to print results. And we learned about formatters last time. So cargo run, and there you see down here, the result was 1. So pretty cool. All right, as an example, let's change one of our enum variants to hold data inside it. So these right now, they don't hold anything. We saw examples of them holding strings, so we're gonna put some data in there. From 1999 through 2008, the United States minted quarters with different designs for each of the 50 states on one side. Yo, who remembers collecting those? If you collected those, you were cool, right? I was. All the kids at my cool table at lunch all collected them. We were all really cool. No other coins got state designs. So only quarters have this, so those values have this extra value. We didn't give state pennies. There were no state nickels. That's what we're saying here. We can add this information to our enum by changing the quarter variant to include a US state value stored inside it, which we've done in listing 6.4. So I'm not going to write out all the states, but let's do what they did and just, make 2 states. We're going to use the 2 real states. We're going to say enum US state. We're going to go with New York, New Jersey, classic. That's it. Anyone from other states? We'll put it in there. I know we got Florida in the chat. We got Long Island, which is its own thing. No, go Florida. All right, so now what we'll do is we'll associate our quarter with a US state. Let's imagine that a friend of ours is trying to collect all 50 states. This is close to home. A friend of ours is collecting state quarters, what we just talked about. While we sort, and the friends at my table, we all collected the quarter. We'd also be writing programs. It's just the kind of cool jocks we were, While we sort our loose change by coin type, we also call out the name of the state associated with each quarter. So if it's one of our friend doesn't have, they can add to their collection. Like, I got Hawaii. Who's got Hawaii? I had Hawaii. In the match expression for this code, we can add a variable called state to the pattern that matches values of the variant coin quarter. So we can break it down further. When a coin quarter matches the state variable, we'll bind to the value of that quarter state. Then we can use state in the code for that arm like so. So we're actually going to accept the state there. So let's change our code here. So quarter now accepts state, and we're going to go ahead and expand this a bit. So let's do this. And we're going to go ahead and print state quarter from, and again, this is the formatting that we talked about. We can make it pretty, right? We could do this, make it pretty. We'll do that. And we're going to pass state. So now let's try constructing a quarter here. We'll do Jersey equals coin quarter New Jersey. And then we will call let's just copy this down here. We'll do let result, value and cents, and we'll pass it Jersey. The result was results. And we will call, let me clear this out so you can see it up top. Let me move myself to the bottom left so I'm out of your way. And we'll do cargo run. All right, so check it out. So we got that's because I put that formatter like a fool because I expected it to work. So let me just go down here, get rid of this formatting. All right. And let's go back here, clear that out, cargo run. Not found in this scope. New Jersey. That's because we need to create New Jersey. So what we'll do here is we'll say Jersey equals, well, we actually don't need to do this. What we can do is we can do this, US state, New Jersey. Clear that out, cargo run. Expected enum coin, found enum US state. Because I have to do that here, not there. Get rid of that, paste that there. Value and cents, pass it Jersey. There we go. Cargo run. Ooh, what did it say now? U.S. state cannot be formatted using blah, blah, blah. Let's see if it knows that that's a thing. No, it doesn't call that out. So they formatted state like that. Let's see if we can get this to work. So let's look at the clues. Debug is not implemented for U.S. state. Add derived debug. Remember this? They did it up here. So we can inspect the state. So let's do that again. So this will allow us to actually format it in that way. So we add this to our enum. Derived debug. Now let's try it. That means that it has the trait where we can actually debug it. So there we go. State quarter from New Jersey. The result was 25. Awesome. Pretty nifty. All right. In the match expression for this code, we add a variable state. When a quarter matches the state variable, we'll bind to the value of the quarter state. Then we can use state. So we just saw that. Awesome. If we were to call value and cents coin quarter US state Alaska, coin would be coin quarter US state Alaska. When we compare that value with each of the match arms, none of them will match until we reach coin quarter state. At that point, the binding for state will be the value US state Alaska. We can then use that binding in the print expression, thus getting the interstate value out of the coin enum variant of the quarter. So pretty cool. And again, we've seen stuff like this. In our guessing game, this is pattern matching. Here we're getting the number out. Here we're not using the error, but we could have. But it's just showing that's very similar to what we've done there. So very awesome. All right. Matching with option T, so with the generic option, which we learned about. In the previous section, we wanted to get the inner T value out of the sum case when using option T. We can also handle option T using match, as we did with coin. Instead of comparing coins, we'll compare the variance of option T, but the way that the match expression works remains the same. So we're going to be looking at the different options that can come out of T. So the sum or the none. Let's say we want to write a function that takes option signed 32-bit integer. And if there's a value inside, it adds 1 to that value. So it checks it. If there's a value there, it adds 1 to it. If there's not, we'll see. If there's not a value, the function should return the none value and not attempt to perform any operations. This function is very easy to write thanks to match and will look like this. So pretty cool. So let's do that here. We've called this coins, so we put ourselves in kind of a pickle here. So what we will do is we will create a new, let's see if we're gonna do more of this stuff, because then I'll just create, no, all right. So we'll just call this next one cargo new. And we also don't have to make new ones. We could just make single functions and just compile them, but it's fun to exercise our cargo new. And so what we'll do is we'll do option match. Cool. Go into option match, main, create a function called +1, takes an option of a signed 32-bit integer. It's going to return an option of a signed 32-bit integer, and it's going to match on X, which is the signed 32-bit integer option, so it could be none. If it's none, we just want to spit out none, and that's why we're returning an option. So that's important. If we were going to return anything else from none, right, like let's say we were going to return a number, we wouldn't need option. We need option because we're saying, hey, it could be none. And then otherwise, if it's there, sum I, we're going to return itself +1. And again, we have to wrap it in the sum because sum denotes that it's an option type. If we left off sum and just returned I +1, our return type would be invalid, right? So that's what that's about. So let's now call let 5 equals sum 5. And it's going to infer that it's a signed 32-bit integer. Let 6 equal +1, and we're going to pass it 5. Let none equal +1, and we're going to pass it the none type. And so down here, what we'll do is we'll print ln. We'll say, oh, this is kind of redundant, but 6 is, none is And let's see if it's going to let us print these. 6, comma, none. And let's go ahead and run that. So we'll go into our option match, cargo run. I was wondering what it was going to do because it's going to try to format it, but it is an option. So it might not be there. So how does it format none? It doesn't know how. Check this out. Option I32 cannot be formatted with the default formatter. So it says down here, you may be able to use this or this. So we'll try using that, see if it complains, and then it might just be that we need to use that decorator there. So let's do this. Try it again. Oh, nice, awesome. So 6 is sum 6 and none is none. So it actually prints out that it's sum 6. That's really cool. I like it. Awesome. Let's examine the first execution of +1 in more detail. When we call +1 with 5, the variable x in the body of +1 will have the value sum 5. We then compare against each arm. So none, it's not going to match that. The sum 5 value doesn't match it. So we go to the next arm, sum I. Does sum 5 match sum I? Why, yes, it does. We have the same variant. The I binds to the value in sum. So I takes the value of 5. And so it adds 5 to 6. 5 to 1 gives you 6. The code of the match arm is then executed. Now let's consider the second call of +1, where x is none. So we're actually passing none. So it does match that none block, and therefore it does return none. Thanks for stopping by, Virtual Boza. Appreciate it. Good night, man. So it matches. There's no value to add to it. So the program stops and returns none, right? Combining match and enums is useful in many situations. You'll see this pattern a lot in Rust code. Match against an enum, bind a variable to the data inside, and then execute code based on it. So super powerful stuff. I'm excited to use it. Hope you are. It's a bit tricky at first, but once you get used to it, you'll wish you had in all languages. And from experience, having used it in pattern matching in other languages like Elixir and Elm, literally when I learned those, it is like the first thing where I'm like, wow, this really clicks. This is awesome. I wish I had it. The closest thing we can get, if you've ever used JavaScript and you've used Redux, you have those long switch cases, right, where we're comparing against strings, and we usually make those constants. Redux was born out of the Elm architecture, which leveraged pattern matching on unit types that gave you a similar thing without us having to use string constants. So super powerful stuff, and just a really, really neat way to handle control flow in an application. Matches are exhaustive. There's one other aspect of match we need to discuss. What if it doesn't match, right? What if it doesn't match? Consider the version of our +1 function that has a bug and won't compile. So here we have +1. Again, we have Rustation over here, and she's chilling. She's like, it doesn't compile. And I'm like, oh shit, you're right. +1. X option, signed 32-bit integer, returns an option signed 32-bit integer, match X. Sum I, turn I +1. So we're not handling the none case. So the compiler's gonna yell at us right now. It says none is not covered. So we saw this before when we got rid of error. Error is not covered, none's not covered. So really cool. It's gonna help us. It's gonna make sure we handle those cases. It has to be exhaustive. There's no default here. There's no fallback, right? There's no, whatever, or in JavaScript, there's no default because we have exhausted all the options. If we had an enum with more properties, like if we had a coin, right, and we didn't handle the quarter, it's not exhaustive. And as you add more, your match statements that match on that type or that enum need to be exhaustive. They need to check every option in each of the arms, or it will complain. Rust knows we didn't cover every possible case. So really, really cool. Especially in the case of option T, when Rust prevents us from forgetting to explicitly handle the none type. It protects us from assuming that we have a value when we might have null, thus making the billion-dollar mistake discussed possible. Mission impossible. That's it. The underscore placeholder. Familiar with this? We've seen this. This is what we're going to be talking about here. We got the, so we don't want to list all possible. So this is cool. So we can use it if we don't want to list all possible values as a way to basically grab all, right? Rust is a pattern with the underscore, and this is also in Elixir. I've seen this, and also in Elm, so pretty cool. For example, an unsigned 8-bit integer can have valid values 0 through 255. If we only care about values 1, 3, 5, and 7, we don't want to have to list out all the other values. Fortunately, we don't have to. We can use the special pattern underscore instead. So that's awesome. We don't have to, it's like a catch-all, right? So it's still handling it. It's going to hit that match. It's not just like, so I guess in that way it is similar to default, but it's a catch-all. So let's try that. So we'll create one here. Print only 5s. So print only 5s is a function I'm making. It's going to take x. X is going to be of typed unsigned 8-bit integer. And it's going to return we don't need to return anything. We're just going to have a print only 5. So we're going to match on x. And if x is 5, then we're going to print ln 5. And if it's anything else, we're going to not do anything. So we're going to print nothing. Or we can just, we don't need to do anything. In this case, we'll just return nothing. We'll print out, let's print out. We'll make our function funny. We'll print out just nothing there. So if it's 5, it'll print out 5, otherwise nothing. So if we call print only 5s, oh, don't forget to separate these with commas. So let's go ahead and call print ln, and we're going to call, we don't need to, we can just call it. It's going to print for us. Print only 5s, pass it 1. We'll pass it 5, and we'll pass it 7. And we'll run this program. And it only printed out 5. And it printed out new lines for the other 2. Pretty cool. So we have this catch-all. The unit type is just the unit value. Okay, so the underscore pattern will match any value by putting it after the other arms. The underscore will match all the possible cases that aren't specified before. The unit type is just the unit value. So nothing will happen in the underscore. So that's what we want in our, this is exactly what we want here. We want the unit type. Had I just read? Pretty cool. Nothing will happen. As a result, we can say that we want to do nothing for all possible values that we don't list before the underscore placeholder. However, the match expression can be a bit wordy in a situation in which we care about only one of the cases. For this situation, Rust provides if let. More about pattern matching can be found in chapter 18. Pretty cool. All right. Concise control flow with if let. Who knew that was coming up, right? After that last sentence, they drop it on you like, if you only need one thing, there's this thing called if let. I thought they were going to be like, and you could find out more about that in chapter 10, but no. They popped us right over. They just transitioned. All right, so we're here. The if-let syntax lets you combine if and let into a less verbose way to handle values that match one pattern while ignoring the rest. So kind of like what we did with our match 5. Consider the program listing 66 that matches on option unsigned 8-bit integer value, but only wants to execute code if the value is 3. This is exactly our example. That's what we have, right? In this case, they have an option type, some unsigned 8 value. If it's there, print it, otherwise do that. We want to do something with some 3 match, but don't want to do anything with any other values. So let's change our code really quick to handle this. So what we'll do is we'll say it's going to take an option, right, of, we'll just stick with that. And 5 here will be sum 5. We'll also pass it sum 1. And we'll do sum 7. Pretty cool. Okay, so how are we going to refactor this? And so here, don't forget, we got to change this to sum 5. Let's run our code, see if it still works, so that we don't go ahead without testing it first. We're still good. All right, so let's see if we can change it. Instead, we could write this in a shorter way using if let. The following code behaves the same as the match we just wrote. CCFYI for short. Control flow with if let. Lit. Control flow with if let. I like it. CCF will. CCF Will. It sounds like something we say late night chat when our buddy Will hops in after a few drinks and he's trying to play games. Right? Sounds like something we'd say. CCF Will. All right. So let's change it. Let's try it. So we don't need all this. Let's comment this out and let's do if let sum 3 equals. Oh, well now it's just doing our block there. So we say sum U8 value, and then we're gonna print 5. Oh, we don't want 5. 5. So sum let, we have this sum 5, and we have this little match here, print 5. So the syntax if let takes a pattern and an expression separated by an equal sign. Works the same way as match, where the expression is given to the match and the pattern is its first arm. Using if let means less typing, less indentation, less boilerplate code. However, you lose the exhaustive check that match affords. So what we're doing here is we're saying if it's 5, print 5. So it's assigning the evaluation for this, right, and separated by the equal. So pretty cool. A little less coding. Choosing between match and if let depends on what you're doing in that particular situation and whether gaining conciseness is an appropriate trade-off for losing that exhaustive behavior that the underscore affords. In other words, you can think of if let syntax as syntax sugar for a match that runs code when the value matches one pattern and ignores all their other values. So this is when matches only one value. Pretty cool. All right, so let's see. We can include an else in an if let. The block of code that goes with the else is the same as the block of code that goes with the underscore case in the match. So like, I don't know, we're kind of losing the value then, I feel like. It's equivalent to if let else. Recall the coin enum definitions in 6.4 where the quarter value also held the use state value. If we wanted to count all non-quarter coins, we see while also announcing the state of the quarters, we could do that with match expression like this. So we have a mutable coin starting with 0, match coin. We're saying if it's a quarter state, print ln. So this is the exhaustive version. This is like the standard match, right? Here is the if let syntax. So if it's this coin, print it, right? Otherwise this. I actually prefer this, but let me know what you think in the chat. If you have a situation in which your program has logic that is too verbose to express using a match, remember that if let is in your Rust toolbox as well. So we're going to reach in that Rust toolbox. We're going to look inside and we'll see if let there along with match, and we can pick like, well, which one do we want? You know, that's the benefit. We have the toolbox. We can reference it. It's there. It's in our back pocket. It's another option. When do we use it? We'll see. Maybe if we look at other Rust code where other developers choose to use it, we can get an idea of, some nice areas for it. But pretty cool. Summary. We've now covered how to use enums to create custom types that can be one of a set of enumerated values. Super cool. We've shown how the standard library's option or generic option type helps you use the type system to prevent errors. That's really cool. When enum values have data inside them, we can use match or if let to kind of create some arms to write some code depending on the values. Your Rust programs can now express concepts in your domain using structs and enums. Creating custom types to use in your API ensures type safety. The compiler will make certain your functions get only values of the type each function expects. So that's what we want from a typed language, right? We want that safety. That's why we're using it. It's a little more effort up front, but it pays back in dividends, right? And if any of you have used a typed language, if any of you have converted your JavaScript to TypeScript or have started using TypeScript, you know it's a little more, but you get the benefits. And in some cases, if you're not getting the benefits, maybe in like a language like JavaScript, maybe you're not sprinkling in enough types with TypeScript. And here in Rust, it's going to force us into that ecosystem and provide safety by default, which is very cool. In order to provide a well-organized API to your users that is straightforward to use and only exposes exactly what your user will need, let's now turn to Rust's modules. Wow. Whew. And we are on modules. Chapter 7. Wow. And we still got a good amount of time. Hopefully you're still with me. Max Thacker Codes. What up, Max Thacker Codes? Hello to you as well. Happy to have you. Just finished chapter 6. We're going to hop into chapter 7. Managing growing projects with packages, crates, and modules. Pretty cool. So, let us see. So we've used cargo before, right? We're using cargo. Why are you learning Rust if you don't mind me asking? Great question. I found it a really interesting language. I've heard great things about it. I haven't used a system programming language since using C, and I don't want to write C anymore. So I figured now's a good time as any to learn Rust, and that's why I'm doing it live so that everyone can join me. Just hopefully we get another system programming language in my toolbox. We just talked about the Rust toolbox. I'm hoping to get, if I need to reach for some systems programming, I've heard Rust is the best way to do it. See, yeah, C's a little rough. Rust seems pretty great so far. We'll see. So we've used cargo before. This is like how we've grouped our things. We just use cargo new. It's overkill for what we're doing, right? Because it creates a cargo lock. It creates dependency mappings, right? But it has all the tooling, which has been nice. So let's learn about modules. As you write large programs, organizing your code will be important because keeping track of your entire program in your head will become impossible. We've seen this in a lot of language. By grouping related functionality and separating code into distinct features, you'll clarify where to find code that implements a particular feature and where to go to change how the feature works. If any of you have worked on a project with friends or at work, you'll know that a lot of our job is reading code, right? We write a lot of code, but we read more code. So knowing where to go and knowing where things are and how to find them is a big part of debugging and contributing to a large code base. Programs we've written so far have been in one module, in one file, totally. As a project grows, you can organize code by splitting it into multiple modules and then multiple files. We'll definitely need to do that. A package can contain multiple binary crates and optionally one library crate. As a package grows, and you'll remember to just jump back, crates, cargo, that's what we're calling like libraries. Like we call them crates, and you can import crates. So cargo imports crates. Similar to like JavaScript, where we're importing packages, we call them crates here. Nice. Max Thacker Code says he knows a little bit of Rust, or she, I don't know. Very cool, Max. That's awesome. So a package can contain multiple binary crates, just to cover this again, or one library crate. Pretty cool. As a package grows, you can extract parts into separate crates that become external dependencies. The chapter covers all of these techniques. For very large projects, a set of interrelated packages that evolve together, Cargo provides workspaces. Ooh. And we'll cover in the Cargo workspace section in chapter 14. So we won't get into that yet. It's far ahead. Cemetery Waltz. Rust is great. Awesome. Yeah, I'm excited. I've been loving it. Enjoying it. In addition to grouping functionality, encapsulating implementation details lets you reuse code at a higher level. All right. Once you've implemented an operation, other code can call that code via its code public interface without knowing how the implementation works. This is great, right? So we used to expose public interfaces in something like C with a header file. In other languages, you have public functions, things like that. So that's how you expose your API without necessarily exposing the guts of it, right? So pretty cool. The way you write code defines which parts are public for other code to use, and which parts are private implementation details that you reserve the right to change. This is another way to limit the amount of detail you have to keep in your head. So for example, let's say you have a package you've open sourced and you're using semantic versioning, and you have one API, add, and it adds 2 numbers. That could be your public API, but how you've implemented add, you can keep private. And then when you change the implementation of it, as long as you're not changing the public API, you don't need to up that version. You might want to patch it just to indicate that there's been changes to the code base, but we don't need to change the version, and people that are depending on it are still able to get the same functionality. A related concept is scope. The nested context in which code is written has a set of names that are defined as in scope. Xnowry, thank you for the follow. Appreciate it. Awesome. When reading, writing, and compiling code, programmers and compilers need to know whether a particular name at a particular spot refers to a variable, function, struct, enum, module, constant, or other item, and what that item means. You can create scopes and change which names are in or out of scope. You can't have 2 items with the same name in the same scope. Tools are available to resolve name conflicts. Oh, Cemetery Waltz, no problem. Thank you for the follow then. Appreciate it. So this is important. You can't have 2 items with the same name in the same scope. Tools are available to resolve name conflicts. So that's like, we've seen that, right? So let's imagine you have a Python file, right? A Python module, and you're importing, from blank, import blank. You can't import two things in the same name, and we'll know which one you're calling. Or from JavaScript, if you're doing import some component from somewhere else, you can't have two components you're pulling in from the same name, so you would use import as syntax or something like that. Rust has a number of features that allow you to manage your code's organization, including which details are exposed, which details are private, and what names are in each scope in your programs. These features, sometimes collectively referred to as the module system. So this is what we're talking about, Rust module system. So we have packages, a cargo feature that lets you build, test, and share crates. Crates, a tree of modules that produce the library or executable. Modules and use let you control the organization, scope, and privacy of paths. Paths, a way of naming an item such as a struct, function, or module. So you have path, modules, crates, which is a tree of modules, so it's going up, right? So you have paths, modules, crates, and packages. Build, test, and share crates. In this chapter, we'll cover all these features, discuss how they interact, and explain how to use them to manage scope. By the end, you should have a solid understanding of the module system and be able to work with scopes like a pro, like a true Rustation, right? We're all here. We're trying to Rustation, trying to become the crab, whatever. It's going to be fun. Let's check it out. Packages and crates. Here we go. First part of the module system we'll cover are packages and crates. A crate is a binary or library. The crate root is a source file that Rust compiler starts from and makes it the root module of your crate. We'll explain modules in depth in defining modules to control scope and privacy section. A package is one or more crates that provide a set of functionality. A package contains a cargo.toml and describes how to build those crates. So you can see our cargo, the projects that we created with cargo new also contain a cargo.toml, which have the dependencies. So here our guessing game had a dependency on the random number generator crate. So pretty neat. Let's walk through what happens when we create a package. First, we enter the command cargo new. We've done this many times. So cargo new my project. Created binary application my product package. Then we go into my project and we see it has a cargo.toml. It has a source folder. And if we go in the source folder, we'll see it has a main Rust file. And so we just made one here with our options match. There's our main Rust file. There's our target. That's what is where our build gets. Once it gets compiled, it gets put in target. Again, we're not building for production, so it's put in the debug. And then we have our cargo toml that declares our dependencies. We have no dependencies for this project. And our cargo lock, which will lock the versions of our dependencies. When we entered the command, cargo created a cargo toml file, giving us a package. Looking at the contents of cargo toml, there's no mention of source main because cargo follows a convention that source main is the crate root of a binary crate with the same name as the package. Likewise, cargo knows that if a package directory contains source lib Rust, the package contains a library crate with the same name as the package, and source lib is its crate root. So if we put lib, that'd be the crate root. If we put main, that would be the crate root. And if you put lib, they know that the package contains a library crate. And with main, the crate root, it knows that the crate root is main. So it's a binary crate. Pretty cool. So we have main, binary crate, lib, library crate. Here we have a package that only contains main, meaning it contains a binary crate named my project. If a package contains a source main Rust and a source lib Rust, it has two crates. So we could have both, and it would have two. It has a library crate and a binary crate, both with the same name as the package. So we have the my package, or in this case, in their example, my project library crate, my project binary crate. A package can have multiple binary crates by placing files in the source bin directory. Each file will be a separate binary crate. A crate will group related functionality together in a scope so the functionality is easy to share between multiple projects. For example, the rand crate we use in chapter 2 provides functionality that generates random numbers. So we use that for the guessing game, which you can see here in our cargo toml, we imported the rand crate. We can use that functionality in our own projects by bringing the rand crate into our project's scope. All the functionality provided by the rand crate is accessible through the crate's name, rand. And you can see if we look at our main Rust file here, we're pulling in rand. So here we're saying use the module rand, And in this case, RNG was the method we pulled in. So pretty cool. Keeping a crate's functionality in its own scope clarifies whether particular functionality is defined in our crate or the RAN crate and prevents potential conflicts. So that's important. Keeping a crate's functionality in its own scope clarifies whether a particular functionality is defined in our crate or the RAN crate and prevents conflicts. For example, the RAN crate provides a trait named RNG. So we didn't just say use RNG, we said use RNG from RAND, right? We can also define a struct named RNG in our own crate because a crate's functionality is namespaced in its own scope. When we add RAND as a dependency, the compiler isn't confused about what the name RNG refers to. In our crate, it refers to the struct RNG that we define. We could access the RNG trait from RAND crate as RAND::RNG. So that it has a namespace there, so there's no collision. So if I wanted to create my own struct, and you can see here we're using RAND. If I wanted to create my own struct called RNG, I could totally do that. And that would be fine. Keeping crates functionality. Okay, we just read that. Let's move on and talk about module system. Defining modules to control scope and privacy. This is the section they just mentioned. In this section, we'll talk about modules and other parts of the module system, namely paths that allow you to name items. The use keyword that brings a path into scope, which we've done here, and the pub keyword to make items public. We'll also discuss the as keyword, external packages, and the glob operator. For now, let's focus on modules. Modules let us organize code within a crate into groups for readability and easy reuse. Modules also control the privacy of items. So again, let's look at that. Modules let us organize code within a crate into groups for readability and easy reuse, and they control the privacy of items, which is whether an item can be used outside code, public, or is an internal implementation detail and therefore private. As an example, let's write a library crate that provides the functionality of a restaurant. We'll define the signature of functions, but leave their bodies empty to concentrate on the organization of the code rather than the actual implementation, rather than actually implement the restaurant in code. In the restaurant industry, some parts of the restaurant are referred to as the front of house. It's like that's the tables, the service, right? The hostess stand. And others are the back of house, the implementation, right? The chefs, the sous chefs, anyone who's cooking, the expo folks, right? Front of the house is where customers are. This is where the host sees customers, servers take orders, bartenders make drinks. Back of the house is where the chefs and cooks work in the kitchen, dishwashers clean up, and managers do administrative work. To structure our crate in the same way that a real restaurant works, we can organize the functions into nested modules. Create a new library named restaurant by running cargo new lib restaurant. So that's new. We're going to use the lib keyword there, or the argument. And then put the code in listing 7.1 into source lib to define some modules and function signatures. All right, so let's do that. So here I'm going to go ahead and run cargo new -- lib restaurant. All right, so created that package. And now if I go here, we'll be able to see our restaurant package. Let me just close this, go down here. Oh, I created in the wrong folder. So I'm just going to remove that. There we go. And there's our restaurant. And you can see we have a source lib, which is different. Previously, we had a source main Rust. And you'll see the boilerplate code that it spits out here is already different than that main code. And so we're going to go ahead and change it. So you can see this is the new keyword mod. So let's go ahead and write mod front of house. So this is just a test. We're not going to use this right now. So what we'll do is let's comment this out. Well, let's do the front of house. And we'll do mod. So another module here. Oh, my spacing's off. Hold on one second. Mod hosting, and then we'll have some functions in here, add to waitlist, and we're not implementing them, but we're just going to see how it's structured. Seat at table, and then we're going to have serving, which is also part of the front of house. And that's going to have take order. Again, we're not implementing. We're going to have serve order. And we're going to have take payment. All right, so now we have the serving, hosting, and that's all part of front of house. So we define a module by starting with the mod keyword and then specify the name of the module. In this case, front of house. End place curly brackets around the body of the module. Inside modules, we can have other modules. As in this case with the modules hosting and serving. Modules can also hold definitions for other items, such as structs, enums, constants, traits, or as we've done here, functions. So pretty cool. By using modules, we can group related definitions together and name why they're related. So it's like a nice naming setup, right? Like we're saying front of house, it's a grouping. Programmers using this code would have an easier time finding the definitions they wanted to use because they can navigate the code based on the groups rather than having to read through all the definitions. Sorry. Programmers adding new functionality to this code would know where to place their code and keep the program organized, right? So if you're adding chefs, cooks, you wouldn't put it in front of house. Earlier, we mentioned that source main and source lib are called crate roots. We had main was the binary crate, lib the library crate. The reason for their name is that the contents of either of these two files form a module named crate at the root of the crate's module structure, known as the module tree. So let's look at the structure. Crate, front of house, hosting, add to waitlist, see to table. So that's our module tree for this structure. This becomes crate, just crate. This tree shows how some of the modules nest inside one another. For example, hosting nests inside front of house. The tree also shows that some modules are siblings to each other, right? They're next they're in the same indentation here, meaning they're defined in the same module. Hosting and serving are both defined in the front of house module. Add to waitlist, see to table, both defined within hosting. If a module A is contained inside module B, we say that module A is a child of module B, and that module B is the parent. So child-parent relationship, similar to what we talk about with components. If you've done React on front end, components, we have parent-child nodes. Notice that the entire module tree is rooted under the implicit module named crate, which is our lib.rs in this case, our lib Rust file. The module tree might remind you of your file system directory tree on your computer. This is a very apt comparison. Just like directories in a file system, you use modules to organize your code. And just like files in a directory, we need a way to find our modules, right? We need a way to find them. So that takes us to the next part. Excuse me. Paths for referring to an item in the module tree. So in other languages, we use relative paths, right? When we import. Let's see how we do this in Rust, right? That's why we're here. To show Rust where to find an item in a module tree, we use a path in the same way we use a path when navigating a file system. If we want to call a function, we need to know its path. A path can take two forms. An absolute path starts from the crate root by using a crate name or crate literal. A relative path starts from the current module and uses self, super, or an identifier in the current module. So you can start from the top or start from the current place. Similar to what we do with an import where maybe you do relative path / to go up a directory. Both absolute and relative paths are followed by one or more identifiers separated by double colons. And we see that. So if we go back here to our guessing game, we see that here. The rand, right? We're referencing the RNG module. Here we're referencing the compare module, and there's ordering. Pretty cool. Let's return to our example. How do we call add to waitlist? This is the same as asking, what's the path to add to waitlist? We simplified our code a bit by removing some of the modules and functions. We'll show you two ways to call add to waitlist. Function from a new function, eat at restaurant, defined in the crate root. The eat at restaurant function is part of our library's crate's public API. So we mark it with the pub keyword. So this is something we're going to be exposing. In the exposing paths with the pub keyword section, we'll go into more detail about pub. Note that this example won't compile just yet. We have Rustation, she's there. It won't compile. So let's write this up, knowing that it won't compile, just so we can see how it works. So we're going to create a new public function, eat at restaurant. And we're going to reference that front of house. So we're going to say create, that's our root, front of house, hosting, add to waitlist. It's not going to do anything, but we'll call it there. And then we're going to do a relative path, front of house, hosting, add to waitlist. So you see here the absolute path, relative path. And so let's mark that like they have here. Calling the add to waitlist function using both paths. The first time we call the add to waitlist function in eat at restaurant, we use an absolute path. The add to waitlist function is defined in the same crate as the eat at restaurant, which means we can use the crate keyword to start an absolute path. So that's what we're doing here. We're kicking off an absolute path from crate, front of house, hosting, add to waitlist. After crate, we include each of the successive modules until we make our way to the appropriate function. You can imagine a file system with the same structure where we use slashes. So, yep. The second time we call add to waitlist in eat at restaurant, we use the relative path. The path starts with front of the house, the name of the module defined at the same level of the module tree as eat at restaurant. So eat at restaurant's defined at this root level right under crate, so is front of house. So that's how we can use that. Now, if front of house was nested inside another module, we'd have to use that. But since it's defined at the same level, we can just use the relative path. So pretty cool. Choosing whether to use a relative or absolute path is a decision you'll make based on your project. The decision should depend on whether you're more likely to move the item definition code separately from or together with the code that used them. So if you're more likely to keep it together, then using a relative path kind of infers, hey, this code is here and it intends to stay grouped here. By using absolute path, you're saying this, you can move this code wherever. It doesn't necessarily need to stay grouped in here. It's not explicitly like stating that as a fact, but it's kind of giving that suggestion is what they're getting at. So if we move the front of house module and the eat at restaurant function into a module named customer experience, we need to update the absolute path to add to waitlist, but the relative path would still be valid. However, if we moved eat at restaurant function separately into a module named dining, the absolute path to the add to waitlist call would stay the same, but the relative path would need to be updated because it's no longer in the same place. Our preference is to specify absolute paths because it's more likely to move code definitions and item calls independently of each other. So by using absolute path, you can move stuff around and not have to worry about it. Let's try compiling and find out why it won't compile. Okay, so to try compiling this, we can go over here. We can run cargo. So first we'll go into our restaurant and run cargo check. That'll try to compile it. And so here we can see, let's read what it says. So we have expected value found, hosting, help. Maybe you meant to write a path separator here. So it's pointing, that's my issue. So it's actually pointing out that I didn't write a path separator there. And so that is right here. So that's the first bug there. Let me clear that so you can see. I'm going to move over here. So out of your way. Cargo check. Okay, so now it's saying hosting private module. Module hosting is private. The module hosting is defined here. Module hosting is private. And I'm trying to call it from a public function, I imagine. Boarding due to 2 previous errors. So it's a private function. All right, so let's dig in and see why that is a problem. The error message says that module hosting is private. In other words, we have the correct paths for the hosting module and the actual add to waitlist function we're calling, but Rust won't let us use them because it doesn't have access to private sections. So it can't actually access these because it's private. Modules aren't useful only for organizing code. They also define Rust's privacy boundary. The line that encapsulates the implementation details external code isn't allowed to know about, call, or rely on. So it's the privacy boundary. It's that border, encapsulates implementation details and external code. So implementation details that external code isn't allowed to know about, call, or rely on. So it's the details. You can't directly call on it. Other code, cannot call on it. It's private to that module. So here I'm trying to access hosting, which is a private module of this. That's why I can't access it. So it's a nice way to encapsulate that. And that's called the privacy boundary. If we want to make an item like function or struct private, you put it in a module. The way privacy works in Rust is that all items, functions, methods, structs, enums, modules, and constants are private by default. Items in a parent module can't use the private items inside child modules. But items in child modules can use the items in their ancestor modules. The reason is that child modules wrap and hide their implementation details, but the child modules can see the context in which they're defined. So what that's saying is this can access the child, so the parent modules can't go in and access details of the child modules. The child modules know where they're defined, and they can access ancestors, right? So they can go up and access other things. Because child modules wrap and hide their implementation detail, but the child modules can see the context in which they're defined. To continue with the restaurant metaphor, think of the privacy rules as being like the back office of a restaurant. What goes on in there is private to the restaurant customers. They don't see what happens in the back. That's where they're organizing, setting up the schedule. Maybe they're setting up events. Maybe the social media coordinators back there. Maybe they have a Rust programmer, right? Using Rust to create a web server. You may say, Rust to create a web server? You're crazy. And I might say, well, I visited this website. Are we web yet? And yes, Rust can build a web server, and it's freaking fast. So maybe they're back there in the office building a web server for their restaurant. They want an interactive experience. They're building it with Rust. Maybe we'll dive into that at some point. But that's private, right? That's happening. You're not going to see it. This customer's not going to come in and order and be like, oh, how's the Rust program coming? Is it still working on that? Is it ready yet? Is it web yet? You know, that's not going to happen. There's separation there. So they don't need to know that. Rust chose to have the model system function this way so that hiding inner implementation details is the default. So privacy by default. You may have heard that term. That way you know which parts of the inner code you can change without breaking outer code. So you know it's public and you know it's safe to use this. If you've used JavaScript or you've used TypeScript, you may have checked an object you're debugging and you see some functions are prefaced with underscores, or maybe they're postfixed with underscores, right? That is to denote, hey, don't use this. I haven't understood the use of it. Using it may cause unintended side effects. And you can still call it. And that's because there's no sense of privacy in JavaScript, right? Everything is public in JavaScript. So they do that marker to kind of say, if you call this, it may have unexpected consequences. We have not accounted for said consequences in exposing our API. Don't use it. But here we can actually hide that. We can make it not callable, which is very powerful. And you've used, maybe if you've programmed, you may have seen this in other languages, but pretty cool. So you can expose inner parts of child modules code to outer ancestor modules by using the pub keyword to make an item public. Exposing paths with the pub keyword. So let's see how to do this. Rustation's back. Let's return to the error in listing 7.4 that told us the hosting module is private. We want the eat at restaurant function in the parent module to have access to the add to waitlist. Hoolie's here. Hoolie with the follow. Appreciate it. Poggers to Hoolie in the chat. Thank you for stopping by. You missed our discussion on Argentinian currency, but that's okay. You wouldn't have liked it. We're glad you're here. So we want eat at restaurant function to be a parent module to have access to add to waitlist function in the child module. So we mark the hosting module with the pub keyword. So here we're going to see marking it with the pub keyword. Let's go ahead and change hosting. Mark it with the pub keyword. Save that. It's saying it still doesn't compile. Unfortunately, it results in an error. Let's run it. Let's see it ourselves. Let's go ahead and clear this out. Let's run cargo run. Oh. A bin target must be available for cargo run. Interesting. What did I do here? Well, let's see. Oh, it's because I'm using a library. So that's why we ran cargo check. So my cargo check here is telling me add to waitlist is private. So hosting's public, but add to waitlist is private. So again, you have a public function trying to access a private child, which we know is not possible. So that's what that's about. Now, let's see. Adding the pub keyword in front of hosting makes the module public. With this change, if we can access front of house, we can access hosting. But the contents of hosting are still private. That's why it didn't work there. Sorry, I'm like in the way here. The contents of hosting are still private. Making the module public doesn't make its contents public. Pub keyword of the module only lets code in its ancestor module refer to it. So the error says that add to waitlist function is private. Privacy rules apply to structs, enums, functions, and methods, as well as modules. Let's also make the add to waitlist function public by adding the pub keyword before its definition. So we made this public, but add to waitlist was not public. So we're going to go ahead and say pub. So it's not a module, it's a function, but the public keyword still applies again to what they have here. It applies to functions, enums, structs, and modules, and methods. All right, so now we have pub hosting, add to waitlist, and the pub keyword. Now the code will compile. All right, let's check it out. Let's find out if it will compile. Cargo check, and it compiled. There's some warnings because we're not using these, but it did compile. Pretty cool. All right. Now it compiles. Let's look at the absolute and relative path and double check why adding the pub keyword lets us use these paths in add to waitlist with respect to the privacy rules. So let's see why we can actually use this, why it worked. In the absolute path, again, this first one, we start with crate, the root, librust, this file that we're in right up here, the root, that's crate. Then front of house modules defined in crate root. So then we're at this level. The front of house module isn't public, but because eat at restaurant is public, right here, the front of house, okay, so front of house is public, eat at restaurant is defined, okay, so isn't public, but because eat at restaurant function is defined in the same module as front of house, that is eat at restaurant, front of house siblings, we can refer to front of house from eat at restaurant. So it's in the same module, we can refer to it. So even though it's not explicitly public, it's at the same level, we can refer to it. Next, because they're siblings, right? Next is the hosting module, marked with pub. We can access the parent module of hosting, right? We can access front of the house. Again, even though it's not public, it's at the same level. It's a sibling. So we can access it, and we can access hosting because it's public. Finally, the add waitlist function is marked with pub, and we can access its parent module, so this function works as well. So we have to have pubs all the way down. It's okay to leave it off at the same level. Makes sense. Interesting. May take some getting used to, but makes sense. In the relative path, that's this one here. In the relative path, the logic is the same as the absolute path, except the first step. Rather than starting with the crate root, we're starting with the sibling, front of house. The front of house module is defined within the same module as eat at restaurant, so the relative path starting from module in which eat at restaurant is defined works. So this works, it's a sibling, it's in the same module. Then because hosting and add waitlist are both public, we can call it. So public and private, that's how it's gonna work. Pretty interesting. This is our first time using modules. We hadn't used this yet, so very cool to see how this works. And you probably noticed like back here, we were able to call these functions because they're at the same level, right? They're siblings. So interesting how that works. And again, we're in library, we're in librust, right? Librs. So this is a library crate. And we created this using cargo new with the -- lib argument. So it's a bit different. All right. Starting relative paths with super. So this is the other option for relative paths we didn't talk about. We can also construct relative paths that begin in the parent module by using super at the start of the path. This is like starting a file system path with the .. syntax. Why would you want to do this? So if you're familiar with JavaScript or a language where anywhere we're using relative paths to go up to the parent directory, right? So if you're a file and you want to go to the folder level, use .. right? So that's going to be similar to this. Consider the code below that models a situation in which a chef fixes an incorrect order and personally brings it out to the customer. When that happens, I'm like, thank you. Like that's I'm coming back. That's professional. I love that. But usually chefs are really busy, so they can't always do that. But that's respect right there. I'd give that chef's Twitch channel a follow. The function fix incorrect order calls the function serve order by specifying the path to serve order starting with super. So let's create a new module called back of house. And we have fix incorrect order, cook order, super, serve order. And serve order is in front of house. In this case, they moved it out. So what I'll do is I will go ahead and say, let's make this. They have it. Let's structure it how they have it, just so we're doing the same thing they're doing. So what I'll do is I'll say serve, create a function out here, serve order, and then we'll call super serve order. And then they have another function here, cook order. Cool. The fix incorrect order function is in the back of house module, right? We put it in here. So we can use super to go to the parent module of back of house, which in this case is the crate. So the parent module of this is a crate, which is again our root, which is just librs. Straightforward. From there, we look for serve order and find it. Success. We think back of house module and the serve order function are likely to stay in the same relationship to each other and get moved together should we decide to reorganize the crates. So by saying super, we're saying, hey, keep these grouped together. Don't separate them. We're not using the absolute path here. Therefore, we use super, so we'll have fewer places to update code in the future if this code gets moved to a different module. So let's go over that again. We think the back of the house module and the serve order functions are likely to stay in the same relationship to each other and get moved together should we decide to reorganize the crates model tree. So we'll likely move these together. Therefore, we use super, so we'll have fewer places to update code in the future if this code gets moved to a different module. So pretty cool. Making structs and enums public. So we've seen it with functions, we've seen it with modules. Let's check it out with structs and enums. We can also use pub to designate structs and enums as public, but there are a few extra details. If we use pub before a struct definition, we make the struct public, but the struct's fields will still be private. So again, if we had a struct with, let's say, a temperature and a unit, the temperature and unit would still be private by default. So interesting. We can make each field public or not on a case-by-case basis. So that's pretty powerful. In listing 7.9, we've defined a public back-of-house breakfast struct with a public toast field, but a private seasonal fruit. Yo, that's like you go to you've been to the continental breakfast, right? They give you like the muffin and like the fruit, and you're like, yo, where's like how do I get like the eggs? I want bacon. Like, why it's just like fruit in this like yogurt cup? There's like a banana. And you're like, oh man, I really want the eggs and the waffle that person has. And they're like, oh, sorry, sir, that's not actually part of the continental breakfast. That's included with the room. That's part of the actual, you have to order breakfast separately and pay for that separately. So that's like what we got here. Like the public get the toast, we get the continental breakfast. It's included in the room. But if you want like the seasonal fruit, like the good stuff, you want like the bacon, the eggs, you want like that sick waffle, you gotta pay up. So we got the private seasonal fruit. This model is the case in a restaurant where the customer can pick the type of bread that comes with the meal, but the chef decides which fruit accompanies the meal based on what's in season. Oh, that's cool. Oh, Tank. Heard there's a hostel in Cordova that has a good breakfast. Oh, I've heard of the same. We'll have to check it out. Little dulce de leche. So that's a cool situation. So the person can pick the toast. It's a little different than my continental breakfast situation. They're saying, oh, you pick the toast, but whatever fruit comes out, that's what's in season. Chef's going to be like, you're getting blueberries today. You're getting raspberries, Maybe you're going to get a plum. Better be a good plum. I don't want a wacky plum. So that's a good analogy there. So let's make that. Let's modify this a bit. So we have a struct called breakfast. So it's a public struct. So public struct called breakfast. And it's going to have a public, what are the trait? Fields. They're calling them fields. I always confuse that with the other languages. So we're going to have a field called toast. It's going to be of type string, and it's public. You can order your toast, but seasonal fruit, although part of breakfast, will be private. You will not get to choose that. And we will do that. So that's our public struct breakfast. And then summer. So we're creating an instance of breakfast. So let me actually move over here so I'm out of your way again. So we're going to go ahead and create, we have our public struct, public toast, private seasonal fruit, and we're going to use an implementation block down here to create some methods for breakfast. And we're going to create a public function that's going to let us to order the summer breakfast. And we're going to switch it up. We're going to give it, we'll call it fall. What's a good fall fruit? Used to be one. Oh, now it's a great place to work. We have cool spots. Yes. I've seen those cool spots. Sad. But hey, I'm going to come visit as soon as this is over. We're going to get, me and Tank are coming down there. It's going to be fun. Public function fall, because we're in fall now here in US. We're in fall, so I'm going to put fall. And it's going to be, it's going to type string slice, and it's going to return a struct of type breakfast. And the toast is going to be string from toast, and we're letting them pass toast. So string from toast. So whatever toast you pass in, you'll get. So rye, I'm going with rye. If you're not going with rye, you're a fool. And then seasonal fruit, we're going to go with string from. Peaches is going, we're going to go apples. It's very fall. I know it's basic, but apples, yeah, I think of fall, I would go apple picking. We'll go with apples. So you can put whatever toast you want, but you're going to get apples. Or maybe figs. Figs is a good one. Let's go with apples. Okay, so now we're going to create a public function eat at restaurant, which we have, and let's go ahead and modify this a bit. So I'm going to go ahead and comment this out. I'm going to just kind of make a new one, just so we have that in our code history there. And we will do, we want a mutable meal, so it's mutable. Back of house, because again, we can call back of house at the same level. And we're going to, and that's, it doesn't need to be public, it's at the same level. And we're going to say breakfast, and we want the fall breakfast. And the toast, look at this. Everyone knows, right? Look, they asked for rye toast. Everyone knows. There's something about rye bread when toasted, a little bit of butter. Come on, transforms, absolutely transforms. Some of you are ordering the marble rye. Some of you are ordering the seedless cowards. You're cowards, unless you're allergic, but cowards. Oh yeah, butter's key. Butter's key, and it gets like that perfect balance of toastiness where it's not like the bread's gonna crack or crumble like you got like that rye bread that's been sitting. No, it has to have a little bit of give, and you need the seed. You need the caraway seeds. Come on, unless you're allergic. Unless you're allergic, there's no excuse. And if you're allergic, you might have an EpiPen. Come on. All right. So meal.toast. This is gonna give us the toast equals. So it's mutable, so we can change the toast. They're trying to change the toast from wheat. We're not going to do that. We're going to change it to marble rye. Get a little pumpernickel mixed in there. Agreed. The outer part definitely needs a little bit of snap. So we're going to change it from rye to marble rye, which is acceptable. I'm not changing it to wheat. And then we're going to print ln. I'd like, and we're just printing out this. Toast, please. And meal.toast. So again, the reason we were able to change meal.toast is because it was mutable. Right? We created a mutable struct. And let's just comment these out. So here we can see, in this example here, they're saying, the next line won't compile if we uncomment it. We're not allowed to see or modify the seasonal fruit that comes with the meal. So let's first run it with that. Let's try to do that. first, just so we can see. So we're going to do meal.seasonal fruit equals string. Well, it's not a string, right? Is it a string? It was it's a string. So we'll do string from figs. Try to get some figs. Let's see if they'll give us the figs. All right, so we're going to save that. We're going to go over here, clear it out. We're going to run cargo check. It won't compile because I messed up my println function. Classic. And it even told me, it's like, hey, you're supposed to be calling a macro, so include that exclamation point. Cargo check. All right, so here's, it says right away. Well, actually, hold on. I messed something up too. I did toast. Oh, no, wait. Let's see. What did it say here? Toast. That's right. Maybe write a path separator. Oh, here we go. Field seasonal fruit of struct back of house. Breakfast is private, so we can't change it. Doze, welcome to the chat. Getting elite tonight. Messed up print. Yeah, I did. Classic. Thanks for hopping in, Doze. Appreciate it. So it's saying that we can't access it because it's a private field. So let's go ahead and comment that out, and then we'll see if it can compile now. Cargo check, and it's complaining because I messed up the struct. So it says expected one of, and it shows you the different symbols, found a comma, and it's right here, string from toast. So that is here where we have this function, and that's because I messed it up, because I need to specify this is a function that returns a breakfast, but I need to return a breakfast struct, and I failed to do that. I failed you. So let's do that, indent that a bit. All right, so now let's see if it'll run. Cargo run. Oh, sorry, cargo check, because we're using a library. That's why it won't run. And just some warnings, but it did compile. And the warnings are because we're not using everything. So pretty cool. All right, because the toast field in back of house breakfast struct is public in Eat It Restaurant, we can write and read to the toast field using dot notation. Not that we needed to. We all knew we were picking rye toast anyway. So whatever. Notice that we can't use the seasonal fruit field in Eat It Restaurant because seasonal fruit is private. Try uncommenting the line, modifying the seasonal fruit value, and see what error you get. We did that. Very cool. Also note that because back of house breakfast has a private field, the struct needs to provide a public associated function that constructs an instance of breakfast. So it needs to provide this because it has a public field. Oh no, because it has a private field, the struct needs to provide a public associated function that constructs an instance of breakfast. So pretty cool. If breakfast didn't have a function, we couldn't create an instance of breakfast in Eat It Restaurant because we couldn't set the value of the private seasonal fruit field in Eat It Restaurant. In contrast, if we make an enum public, all of its variants are then public. We only need the pub before the enum. So unlike structs, where you can break it down by field, enum's like, nah, if you make it public, it's all public, right? It's all public. So let's check that out. So let's do back of house. We're going to add an enum, make it public. Tizer. We got the soup, not a soup fan, sorry. Salad, public, both are public, so you can pick either one. Maybe we'll go French onion. I'll tolerate that. Okay, and then so our public function Eat It Restaurant, let's change it a bit. So let's go, well, let's leave that part, but then let's do up here, we'll do let order one equal back of house. Again, back of house we can access because it's the same level, it's a sibling. And our enum appetizer is public, so we're going to say back of house, appetizer, soup, order two, and they don't have an associated string, so we're not associating a particular soup with them. They're just, right now it's just soup and salad. We can associate strings with them though, and if you remember to do that, we would add this, right? Or do that. We'll do that in a second. Let's just follow what it has right here first. So order one, and then we'll order a salad. Because we made the appetizer enum public, we can use the soup and salad variants and eat at restaurant. Enums aren't very useful unless their variants are public. It would be annoying to annotate all enum variants with pub in every case. So the default for enum variant is to be public. So interesting. So enums default to being public. Structs are often useful without their fields being public. So struct fields follow the general rule of everything being private by default unless with a pub annotation. There's one more situation involving pub that we haven't covered, and that is our last module system feature, the use keyword, which we've used, pun intended. We'll cover use by itself first, and then we'll show how to combine pub and use. So I wonder if the enum is public by default. So let's try this. Let's make sure this compiles. So it compiles. Let's try taking off the pub because they said it's public by default. Oh. Clan Watson. So it says boarding due to 2 previous errors. Enum advertiser defined here. Oh no, it is private. Wait, so let's read this again. Maybe it's talking about the fields. It would be annoying to have to annotate all enum variants with pub in every case. So the default for enum variants is to be public. Structs are often useful without their fields. Okay. So default's public, but why did it not? Maybe it just means the variants. It means the variants, soup and salad. That's what it's talking about. It's not talking about the actual thing itself. So it'd be annoying to say pub because we're going to keep it all together. That's what it's referring to. All right. So let's look at the next step. Let's look at the use keyword. How much time do we have left? We have plenty of time. 15 minutes. Let's go. Let's dive in. We got the chat here. We got Clan. We got Doze, Hooli, Tank, Cool Dude, who's a bot. Get that person out of here. Mods. Cemetery Waltz. Everybody. We're going in. Let's go. Bring in paths into scope with the use keyword. It might seem like the paths we've written to call functions so far are inconveniently long and repetitive. : For example, in listing 7.7, whether we choose the absolute or relative path to call add to waitlist, every time we want to call it, we had to specify front of house and hosting too. So it's repeating a lot of code. Fortunately, there's a way to simplify this process. We can bring a path into a scope once and then call the items in the path as if they're local with the use keyword. I'm excited. In this below block here, we'll bring the create front of house hosting module into the scope of eat at restaurant function. So we only have to specify hosting add to waitlist to call add to waitlist function. So let's see what that looks like. So we have our module front of house, our public hosting, and our public function add to waitlist. And here before our eat at restaurant function, we're going to call use create front of house hosting. So now we're pulling it in, and then here we can just call hosting. So I'll do that down here. So we'll call it right here. Hosting add to waitlist. So much easier. It's kind of like namespacing. You've probably seen this in other languages if you use them. Much easier than having to call the whole thing. Excuse me. All right, so adding use and a path in a scope is similar to creating a symbolic link in the file system. By adding use crate front of house hosting in the crate root, hosting is now a valid name in that scope, just as though hosting module had been defined in the crate root. So it's almost as if it's defined right under librs. Pretty cool. Paths brought into scope with use also check privacy like any other paths. Makes sense. You can also bring an item into scope with use and a relative path. So we did it with an absolute path. We could have also done it with a relative path. So let's write that here. So we'll say use with an absolute path, and then the relative path would have been something like use front of house hosting, because again, front of house is at the same level. Cool. here is the example of front of house referencing self. You can also bring, okay, so here we are using self instead of super. So creating idiomatic use paths. You might have wondered why we specified use create front of house hosting and then called hosting add to waitlist in eat at restaurant, rather than specifying the use path all the way out to add to waitlist function to achieve the same result. So we could have maybe done create front of house hosting add to waitlist. Although they accomplish the same task, list 711, the first one, this one here, is the idiomatic way to bring a function into scope with use. Bringing the function's parent module into scope with use, so we have to specify the parent module when calling the function, makes it clear that the function isn't locally defined while still minimizing repetition of the full path. If we had just called add to waitlist, it's not clear where it's coming from. So that's a good point. It's idiomatic. It actually indicates some information, right? It tells us where it came from. If we hadn't used that and we just saw add to waitlist, you might immediately look in the file and say, hey, where is that defined? Whereas when you have that use, you know, okay, we're pulling this in from a different place. So pretty cool. On the other hand, when bringing in structs, enums, and other items with use, it's idiomatic to specify the full path. Listing 714 shows the idiomatic way to bring the standard library's hash map struct into the scope of a binary crate. So here we're pulling in standard library, collections, hash map, and then we're creating a new hash map. There's no strong reason behind this idiom. It's just the convention that has emerged, and folks have gotten used to reading and writing Rust code in this way. So it kind of evolved over time as people use the language. This is what developed, and it's pretty commonplace now. The exception to this idiom is if we're bringing two items with the same name into scope with use. So maybe hash map comes from standard collections, but maybe there's another library that has a hash map. So Rust wouldn't allow bringing them both in with the same name. Here's how we bring in two result types into scope that have the same name but different parent modules and how to refer to them. So here we're bringing standard format and standard IO. Both have a result, but we're specifying the parent explicitly so that we can use them both. So pretty cool. As you can see, using the parent modules distinguishes the two result types. If instead we specified use standard format result and use standard format result, we'd have two result types and the same scope, and Rust wouldn't know which one is the one we meant. It would be confusing. Pretty cool. Providing new names with the as keyword. So this is something we talked about a little bit earlier. This is something, if you're familiar with JavaScript importing, you may have come across this at Python as well, right? So if you have two modules with the same export, so let's talk about Python really quick. You have a function in a Python module called employee, and then you have a function in another Python module called, the method is like employees v2, and it exports an employee, right? An employee class. So you have the employee class from employees.py, and you have the employee class from employees v2.py. This is a real scenario, by the way. Who knows what I'm talking about? You can import both, and you wouldn't say import, you wouldn't say from employees.py import employee, from employees v2.py import employee. You would want to differentiate them. So then you could say, for example, import, or you could say from employees v2.py import employee as employee v2. So it gives you a way to differentiate. And so I'm sure that's what we're going to see here. And JavaScript has that as well. Yes, Uli, of course. I didn't forget Python. The Python love is real. So here we have use standard format result and use standard IO result, and they've namespaced IO result as IO result. So it's a nice, easy way to namespace that thing so that you don't run into the collision. Pretty cool. It won't conflict. Re-exporting names with pub use, so public use. When we bring a name into scope with the use keyword, the name available in the new scope is private. To enable the code that calls our code to refer to that name as if it had been defined in that code's scope, we can combine pub and use. This technique is called re-exporting because we're bringing an item into scope, but also making that item available for others to bring into their scope. So it's like you're importing something and then exporting it. Sounds familiar maybe? If you've used JavaScript, maybe you've written an index.js that imports modules just so that it can export them at the root, right? It gathers a bunch of modules. Export default as maybe you've used. So maybe you have an init.py that imports a bunch of stuff and exports it. So here we're seeing mod front of house with a public mod hosting. That module has a public function add to waitlist. And here we're saying pub use crate front of houses hosting and pub function eat at restaurant hosting add to waitlist. By using pub use, external code can now call add to waitlist function using hosting add to waitlist. So it's saying we're going to use it internally and you can also use it. So pretty cool. If we hadn't specified pub use, the eat at restaurant function could call hosting add to waitlist in its scope, but external code could not take advantage of that nice new shorthand path. So let's put pub here. I'm just gonna make a copy here. I'll say use public use that other scopes can take other external code can take advantage of. Pretty cool. And here we'll just comment that out. Re-exporting is useful when the internal structure of your code is different from how programmers calling your code would think about the domain. Right? Maybe you have some internal knowledge, but you don't need to expose the inner workings, but it's useful for people who are working on the code. For example, in the restaurant metaphor, the people running the restaurant think about front. This is perfect. I love that they use this metaphor, by the way. I've used this to describe back end and front end, like, server, but in this case, it works really well, right? The people running the restaurant may think of stuff as front end of house and back of house, but customers visiting the restaurant probably won't think about the parts of the restaurant in those terms. With pub use, we can write our code with one structure, but expose a different structure, right? How often do you go to a restaurant and sit down and you're like, oh, I love the front of house of this restaurant. The service was great. The hostess was great. Now you talk about the restaurant as a whole, right? A cohesive experience. You say the service was fantastic. The food was fantastic. Some people might, if you have a restaurant experience. I'm not going to speak for everybody, but I like that they called it out like that because that's definitely how I would think of it, a cohesive experience. Doing so makes your library well organized for programmers working on the library and programmers calling the library. That's really cool, right? Very cool. Front of house. Woo! Front of house sexy. Yes, Doze boy. Absolutely. I loving the use of the emojis. Very good. All right. So using external packages. In chapter 2, we programmed a guessing game project that used an external package called rand. You can see that here. If I open up my guessing game, here's guessing game. We imported rand. And again, we declared it as a dependency here in our cargo toml. And we pulled it in right here like this. And we used it just like this. I'm sure this is an exported path. In chapter 2, here's our toml. Adding rand as a dependency in cargo toml tells cargo to download the rand package in any dependency from crates.io and make rand available to our project, right? Then, to bring rand definitions into the scope of our package, we added use lines starting with the name of the crate, rand, and listing the items we wanted to bring into scope. Recall that the generating random number section in chapter 2, we brought the RNG trait into scope and called the rand thread RNG function. So here you can see that, and you can see it here. We did it right here, right? Brought this in and called this. Members of the Rust community have made many packages available at crates.io. We'll pull this up for viewing in a second. And pulling any of them into your package involves these same steps, listing them in your cargo toml and using the use to bring items from the crate into the scope. Note that the standard library, std, is also a crate that's external to our package. So the standard library is external because the standard library is shipped with the Rust language. We don't need to change the cargo toml. We're not installing it from crates.io. It's shipped with the language, but it's outside our scope. But we do need to refer to it with use to bring the items from there into our packages scope. For example, with hashmap, we could use this line. So pulling in hashmap from the standard library. This is an absolute path starting with standard and the name of the standard library crate. So standard is the name of the library crate. In our case, remember, we are in our scope, we called it crate. Using, excuse me, let's see how much time we got. All right, let's see if we can get through this section and then we can end it there. But I think we've made good progress. Using nested paths to clean up large use lists. If we're using multiple items defined in the same crate or same module, listing each item on its own line can take up a lot of vertical space in our files. For example, these two use statements we had in guessing game bring items from standard into scope. So we have use standard compare ordering, and we have standard IO. And we use both of those, ordering, and we used IO. Instead, we can use nested paths to bring the same items into scope in one line. We do this by specifying the common part of the path, followed by 2 colons, and then curly brackets around a list of the parts of the path that differ. That's pretty cool. So it's like you're finding the common path part, and then where it differs, putting curly brackets. So let's do that. I like that a lot. So here we're saying this, and then we're saying compare ordering, and then just IO, what was on its own. So that's super neat. And then we can get rid of that. That's pretty cool. In bigger programs, what happens when we have many? Maybe we break it up onto different lines, but like with the brackets. So similar, like if in JavaScript, when we have an import statement, right? We can import default, but you can also import subparts, and we have the curlies from the same file. You don't need to put each line, import this from this file, import this from this file, import this from this file. And same thing in Python. Nice shorthand syntax. In bigger programs, bringing many items into scope from the same creator module using nested paths can reduce the number of separate use statements needed by a lot. We can use a nested path at any level in a path, which is useful when combining 2 use statements that share a subpath. For example, 719 shows 2 use statements, one that brings in standard IO, and the other brings in standard IO write into scope. So these two. The common parts of these 2 paths are the standard IO portion, and that's the complete first path. To merge these 2 paths into one statement, we can use self in the nested path. Oh, pretty cool. So self is going to refer to IO. Awesome. The glob operator. The glob. If we want to bring all public items defined in a path into scope, we can specify that path followed by the star glob operator, right? Import star as. We've done this in, you've seen this in JavaScript. We used to do it a lot with React. Import star as React, right? Importing everything. So here we have use standard collections. We're importing all publicly exposed items from collections into our scope, right? The use statement brings all public items defined in standard collections into our current scope. Be careful when using the glob operator. It's going to pull in a lot. Glob can make it hard to tell what names are in scope and where a name used in your program was defined. So you might end up with one of those conflicts, right? If you pull in everything, you might have pulled in a result, not known it, and now you're trying to use result somewhere. So good to know. The glob operator is often used when testing to bring everything under test into the test module. We'll talk about that in how to write tests in chapter 11. That'll be cool. That would have helped us a lot with our Celsius to Fahrenheit and a lot of our little exercise functions like Fibonacci. So I'm excited to do that. The glob operator is also sometimes used as part of the prelude pattern. See the standard library documentation for more information on that pattern. Awesome. All right. We're almost done. Let's wrap it up. There's not much more. Just this little part. Go a little bit over. Everyone cool with that? If you can't hang, that's fine. You can catch it on YouTube later. Separating modules into different files. So far, all the examples in this chapter have defined them in a single file. What if we want them in separate files? For example, let's start with the code from 717 and move front of house module to its own file by changing the create root file so it contains the code below. In this case, the create root file source lib, but this procedure also works with binary crates whose crate is main Rust. So let's do it. So we're going to create we'll go back to our lib. Let me close this. So we have our lib here. We have front of house. We're going to move that into its own file. Oh, okay, wait. So it says, and move the front of house module into its own file, front of house. Okay, so let's create a new file. Out here. So we have, let's close this. Close that. We have restaurant. Front of house.rs, and let's move our lib code there. So let's take this out. All right, let's paste it here. Save that. Front of house gets the definitions from the body of front of house module as shown in listing 7.2. Oh, so we actually can leave off the module because it's going to get that from the root, right? Front of house, it's going to get that crate name. So we can drop that initial outer scope thing there. And then let me just go ahead and delete all of this nonsense. Whoa, my Vim stuff is all wacky. I need to adjust my Vim bindings. Let me just do this. This will be easier. Oh. Let's go ahead and grab this. All right. It'll clean up when I format. For some reason, my indentation is wacky. All right. That'll do. So put that. All right. So we have our module. Again, we don't need to declare front of house outside because it's in the front of house file, and that's where it's going to get its name. Definite inside front of house module. Using a semicolon after mod front of house rather than using a block tells Rust to load the contents of the modules from another file with the same name. So we're going to go back to lib, and we're going to load, we're going to say mod front of house, and that's going to pull in from our front of house. All right. Pretty cool. Front of house pub mod hosting. Then we create a source front of house directory and a file front of house hosting rs. So if we want to split it out further. To continue with our example and extract the hosting module into its own file as well, we'll change front of house to contain only the declaration of the hosting module. So we can do that here. So we go to front of house. We can just have it contain the definition. So I'm just going to comment this out for now. So we're just modularizing, breaking it up by file. So we're going to say pub mod hosting. Pretty cool. And we're going to create a front of house directory and a file called front of house hosting. So let's do that. So let's go here. Front of house. Add a module called hosting.rs. And we're going to move this code here, just this little piece here, into here. And hosting just has these two. They're not defined yet. We should move that there. The module tree remains the same, and the function calls in eat at restaurant will work without any modification, even though the definitions live in different files. This technique lets you move modules to new files as they grow in size. Note that pub use create front of house hosting statement in source lib also hasn't changed. So let's make sure this compiles. So I'm going to save that. We have front of house here. And we have this here. So let's check that it compiles. So let's see. Pub function eat at restaurant, aborting due to previous error, could not compile restaurant, expected one of pub use front of house hosting. So let's take a look at where that is an issue. So front of house, we're exporting pub mod hosting. From hosting, we're exporting, we have this pub function add to waitlist, and lib is using mod front of house. And here, the crate we're importing is, so we need to do crate, because it's not in here anymore. Create front of house hosting, and let's see if that works. Pub function eat at restaurant. It's saying is, let's see, could not compile restaurant, unexpected token, and that's because this is unexpected because we forgot to put a semicolon. Classic. All right, so now let's try it. Clear and cargo check. Perfect, it compiled. Awesome. So in summary, let's wrap it up. Chapter 7, made it through Chapter 7. Rust lets you split a package into multiple crates and a crate into multiple modules, and you can refer to items defined in one module from another module. You can do this by specifying absolute or relative path. These paths can be brought into scope using the use statement, so you can use shorter path for multiple uses of that item in the scope. Module code is private by default, but can make definitions public by adding the pub keyword. In the next chapter, we'll look at some collection data structures in the standard library that you can use in your neatly organized code. Awesome. All right, so if you're still with us here, we made it through Chapter 6 and Chapter 7 tonight. Awesome job. Thanks for hanging out. We're going to end it here. We'll do Chapter 8 next Tuesday, 9 p.m. Eastern Time to 11 p.m. Eastern Time. Thank you for hanging out today. Again, if you missed any of the previous chapters, You're going to find those right here on the YouTube channel where we have all the parts. I will upload this part as well. I'll be pushing up the code we wrote today to the GitHub repo, Learn Rust Live. You can find it here. GitHub light mode's killing me. Follow on Twitch if you're interested in getting updates for when I'm going live. If you're liking the YouTube channel, love to hit the subscribe button. That'd be awesome. Clam Watson with the thumbs up. Appreciate it. Appreciate the follow today, Cemetery Waltz and Hooli. That's awesome. Check out the videos. This video, like I said, will be up tomorrow. I'll post it tomorrow, and I'll tweet when it's out and live. And that is it. So again, thanks for hanging out. Really appreciate it. Yeah, right. Loved the jokes in the chat. Loved everyone participating. Super fun. Thanks for coming on board, learning Rust together. We're really starting to learn it. We've got enums, structs. We have a lot in our toolbox now. We have control flow with the match keyword. We know how to structure our project. Now we're going to learn next about some data structures. I'm excited for that. Again, if you didn't catch up, check out YouTube. It's all going to be there. You can watch it on like 2x speed. I'll sound like a chipmunk, but it'll be great. So absolutely appreciate it. And no, don't worry. It's not included in the, it is archived, not included in the YouTube video though, so don't worry. So thanks everybody. Hope you have an awesome night. Thanks for joining me on my Rust adventure, and I'll see you next Tuesday, 9 p.m. Eastern to 11 p.m. All right. Take care. Everybody have a good night.